Well, hello everybody. This is the big night, right? I think there's something I couldn't remember over the weekend happening today. Can you refresh my memory?
Bob Marley's birthday.
Oh, is that all it was?
I don't know.
Is it?
Yeah.
Here's our agenda for today. So most of the class period will be taken by your taking test 1. And sometimes after you've studied before the test, maybe some little things come up. So I always check to see if there's anything you want to ask. Of course, if you ask me something that I know is not on the test, I just say, well, that's not on the test, so we won't talk about it right now. Fair enough? Rather than spend all kinds of time on something I know is not on the test anyway. Because you can't cover every little detail. But you know what's going to be on there basically. I mean, you're going to have to do some integrating, right? I bet you there's a problem about substitution. I bet there's one where you have to use parts. I bet you have to do a trig sub too. Probably even a partial fraction. You know what the big thing is on partial fraction that's easy to miss? You got to check the degree on top and bottom, remember? You can't break it down unless the degree on top is smaller than the degree on the bottom. What do you do if it's not? Oh, long division first. Easy to forget to do that, and then it gets kind of messy if you forget. So.
Is there a long division one? Are you gonna have to do it on there?
I suspect that could happen, yeah. You're good at long division, aren't you?
We'll see about that.
So when do you use long division first? The degree in the numerator is bigger or equal to, okay? Greater than or equal to. And I'll bet you'll have to do a couple of approximation of integrals using one of those Simpsons trapezoid or midpoint or something. But you're ready to roll on those, right? Yes?
Does 5 round up or down?
Well, depends on the context.
Okay, if we have to round to X number of decimal places and X plus 1 is 5, does that round up or down?
I accept either.
Okay.
Because it depends on the situation. So if it's a 5, if you round up, I'm good. If you round down, I'm fine.
Okay.
But usually hear it's
Oh, really?
What was that?
Found out I've been rounding wrong for 24 years.
Well, typically 5 goes up.
Yeah.
But you could argue that it's right in the middle. I mean, who says whether it should go up or down? And for some people that makes a big difference. For me, it's whatever.
Okay.
Any other questions anybody has? Yeah.
Do you think you could do an example of long division real quick?
Maybe I could do the one on the test.
That'd be a great idea.
Deal.
You know, and I would too if I could do that one, but that's the one I got wrong. So I'll have to pick a different one. Let me look in the book and see if I can find one in a minute, okay? Let me see. This stuff was in section 7.4. So I'm on page 493. Looking for one where you have to do long division first. Let me see if I can find one.
I think number 1 on the review had long division in it.
Oh, did it?
I think so.
Okay, we can do that one.
Did it?
I don't remember.
No,
Oh.
has to be long division.
Well, I did long division on that one.
I mean, if you do long division, it doesn't mean you're gonna get it wrong. It might mean it's just a little more effort than you had to put into it. The one that I see here would be 15. So we can check that one out. That's 15 on 493, but I'll write it on the paper here. Okay, on 15, they want you to integrate from 3 to 4. Of course, that's irrelevant to what we're talking about right now, whether it's a definite or indefinite. Okay, I believe I copied that right. That's what it looks like in the book. So when you look at this, you see it's a rational expression. So right away you start thinking, probably partial fractions to make this fly. You notice they're both cubics. Now if the top was quadratic, highest power is a 2, you could just go to your partial fraction. So the first move on this one is to take the denominator and divide it into the numerator. And we add placeholders, just like we did back in algebra class. That make sense? Then you take the first term of the dividend, which is x cubed, and divide by the first term of the divisor. What's x cubed divided by x cubed? So I'm already way down there with a constant, and you get x cubed minus 2x squared, which is kind of weird. Then you subtract. What's x cubed minus x cubed? What's negative 2x squared subtract negative 2x squared? 0. And so you drop this one down, that's still 0x, which doesn't contribute, and then minus 4. So it's a little bit weird. But when you actually do the division of that, the quotient is 1. And then you go minus 4 over the divisor, because that's the remainder. And that's what it turns into.
Okay, thank you.
And then this one can be done with partial fractions. That one, of course, is easy to do, because the antiderivative of 1 with respect to x is just x. So then you proceed to, factor this x squared. This is kind of a nice problem, because that's the nice factors on the bottom. Oh, just to make sure you're going to be okay, let's go one step further and tell me how you would try to split this up. No, you're trying to get the a, b, and c for the partial fractions. You see, this is 4 over x times x minus 2. So you could have an a over an x, but you could have a b over the x squared. If x squared is there, you could either have an x on the bottom or an x squared, because it's a common denominator for both. And then you could have a c over x minus 2. Okay?
48.
Yes?
The b doesn't have to be linear. That doesn't have to be bx plus c.
No.
Okay.
Not when a factor is just squared.
Oh, but if it was x squared plus 1?
Yes.
Okay.
Yep. If you happen to put, bx plus c here, you'd be fine. It's just that b would turn out to be 0. And you have a little more work to do. Okay, was there anything else relative to the test that you wanted to just double check on?
24 maybe.
24 from the review?
Yes.
So you looked at my solution and didn't like it, huh? That was where you had e to the x cosine of x dx, that one? Okay, that's one of that cyclic variety. Because of the product here, we do it by parts. And what do we let u equal?
Something that was easy to integrate,
They
right?
both are.
Yeah.
So you know what is probably true? Probably doesn't really matter, but
Not in this case, at least.
because they're both easy to differentiate and they're both easy to integrate. But what do you think?
Easier to integrate.
Well, let's try this. Cosine of x and dv equal e to the x dx and just see what happens. What's the du then?
Negative sine of x.
And v, of course, is right back to
Of x.
e to the x, right? So when I continue, it's uv, which is e to the x cosine x, right? And then it's minus the integral of e to the x minus sine x, be careful, dx, right? Which is really e to the x cosine of x plus e to the x sine x dx. Okay, but then we have to do that one, and we say, well, how do we do that? Parts. You could let u equal e to the x, and you could let dv equal sine x dx.
The only reason why you put a subscript on your was for tracking purposes, right? Just so that you can.
I put what?
A subscript.
Yeah, because I didn't want you to confuse the u's. So when I said I used it twice, then I say, I quite often do that, and then you don't think it's the same one as before. What is du2 then? Well, e to the x. What is v2? Negative cosine x, right? Anyway, to make a long story short, this thing becomes one of those things called a cyclic. It goes in a cycle. Because if you continue, you have the e to the x cosine of x, which you don't want to lose. And then as far as the integral part goes, you have to go uv, which is minus e to the x cosine x. But then you have to go minus the integral of v du. Well, you see that minus there again. So I'll just make this plus. And what happens?
Turns back into the original.
To cancel on there, yep.
Now this is not good because that was equal to this. And now if I subtract that from both sides, I just get 0 equals this, which is obviously true.
But then.
And that means when I picked my u2 the second time, I should have stuck with what I did before and let the u2 be the sign. In other words, be consistent. And let the dv be the e to the x again. But when you have a cyclic situation like this, you know, let's just say this ended up minus, that would be good. Then you can add it to both sides, and then you get 2 of those equals this, and then you just divide by 2. Okay?
So you want to be what? Consistent?
Yeah, if you, in the first one, we couldn't really decide what should be u and what should be dv, and it didn't seem to matter. But I wanted you to see what happens if you pick u to be the trig function here, and the dv to be the e to the x. Then over here, don't switch.
Okay.
You should let the u be the trig function again. And the dv should be the e to the x. Just be consistent when you do it the second time. Okay. Is that good enough? I mean, get the idea? In other words, we call it cyclic because you just keep ending up back to the beginning, and if you keep doing parts, you're never going to finish. You get into that endless loop. But once this matches the other side, you can use algebra, add it to both sides, or subtract it, whatever, and then...
So if you would have chosen the other one, you would have ended up with a negative instead of a positive?
Different U choice?
Yeah, I think so. Let's try it. Let's let u2 equal the sine of x dx, and the dv to equal the e to the x. No, not that. The dx goes here. Okay, then the derivative would be cosine of x dx, right? And the v2 would just be e to the x again. So then I get the product of those two, which is e to the x sine x. I still have this e to the x cosine of x from before, you recall, right? And then I'd go minus the integral of e to the x cosine of x dx.
And that's where you get.
And now I'm going to be fine because on this side I have e to the x cosine of x dx. Now I can take this and add it to both sides. So I get 2 of these equals that, and then just divide by 2. And I have the value of the integral. Cyclic variety. Goes in cycles. An infinite loop. Okay, anything else you wanted to check?
48.
48? All right. Okay, what was 48?
The integral of negative, from negative 1 to 1.
Of dx over x squared minus 2x. Okay, this is one of these improper integrals because it has a discontinuity in this function at where? At 0. Can you see that? If you let x equal 0, which is right in the middle of that interval there, it becomes undefined. And that's why it's an improper integral. And so we set it up as the limit as t approaches 0 from the left. And then you do the integral from minus 1 to t of dx over x squared minus 2x. And then you add to it the limit as t approaches 0 from the right. This time you go from t to the other limit, same thing. Now this one was a little heavier because now to keep going you got to use partial fractions. I didn't do that to you on the test. In other words, once you got the limit and everything set up, you'll find that the integration is fairly easy, but you had a question.
When you have a discontinuity improper integral, do you always have to do from the right and the left?
If the discontinuity is inside the interval.
Okay.
Now the other kind is when you had maybe minus 1 to infinity or something. Then you just have to do 1 the limit as t goes to infinity.
Because you cannot really approach infinity.
Right, from both sides. So only if the discontinuity is somewhere inside the interval do you need the 2 separate limits, one coming in from the left and the other from the right. Okay?
Well, that kind of does it for me then.
But like I say, you're going to find on the test, once you get this far, you're going to find the integration to be pretty easy. In other words, I'm not going to make you do another partial fraction to finish it. But it wasn't bad for the review because you got a chance to review another partial fraction in the process. Yes, sir.
I have a question about that one too.
This one, yeah.
You like disregarded the left integral because you said that because in the end it's going to be like natural log, and natural log can't be a negative.
Right.
But it's the absolute value of natural log, so couldn't you technically do that?
But when you put -1 in there, what do you get?
Well, for right here, you said the domain of natural log of x is 0 to infinity. Isn't it actually negative infinity to infinity? Because no matter what you put in for x, you're going to take the absolute
But
value.
that's not why I did it. When I went to the partial fraction, see, it's x and x minus 2.
Yeah.
And then when you split it, you're going to have an a over x and a b over x minus 2, aren't you?
Yeah, and then you solve for a and b.
Right.
Right.
But
I get that.
right here, when you end up with a natural log of absolute x, right?
Yeah.
And it's going to be from -1 to t.
Yeah, I got that. But couldn't you put a -1 in there, and then it would just...
Then it becomes 0.
Right, but I'm saying, I got that, but, so technically you could do that, but here you just kind of like disregarded that whole left side. Because you say we will examine only the second limit. Why? Why did you say we only wanted to examine the second limit?
Oh, because this isn't going to contribute.
Okay, because it's... Alright, I guess I get it, but...
Yeah, I was trying to save a little room because I was running out of space, but
Okay.
I didn't mean to confuse you.
No, it's fine.
But I examined that side and it didn't contribute, so I just wanted you to see where the answer came from.
Okay, yeah.
I shouldn't do that, sorry.
So you did go ahead and find it, and then you figured, oh, it's no good.
Right. And I thought, well, you should find the same thing. I didn't expect you to just see it. I was, I just work it out and see that it wasn't going to contribute. Okay?
No, that's what I did. I did like the whole thing, but when I was checking, I was like, well, where did that second or the first one go? I got understand.
It's on my scratch paper, which didn't fit there. Anything else you were wondering about? Yes.
Even-powered sine and cosine trig integrals? Or is it like, I did see one on the reviews, I was wondering if you like go over one real quick.
I didn't make you do one on the test, but I'll go over one if you want to.
Oh, I'll get that. This is,
In other words, you don't have to do just a plain cosine squared or plain sine squared. I mean, I would love to have you do that, but I don't want the test to get so long that you never leave.
On those ones, you try to pick the one with the U sub, because you try to put in U sub, right? You pick it with the even power.
Are you
Yeah.
gonna have long division?
Wait, you do pick?
Yeah.
Yeah, we went over that earlier, just before you got here.
Are we gonna have to complete the square?
Oh yeah, we should go over that.
Yeah, I did put one of those on. We have to complete the square. That's easy, isn't it?
Yeah, those ones should be.
I did something else too. I shouldn't even tell you, but on the integrals, I said, here's a bunch of them to do. I think there's 6 of them, and you have to do 5. So if there's one you really, really hate,
You can avoid it.
you say, I don't want that one.
Is that the extra credit then?
Well, if you do all 6 right, I always give you extra credit, yeah.
if you get one up on where
Yeah.
Well, then I just scratch the worst one.
Sweet.
So you can't lose. So, did you want to check completing the square one? Or not? I mean, it's up to you, but... Let me see. one of those was, I'm over in the trig subsection. That's on page 483, and I'm just looking for one. 24 is one of those, where you have to integrate dt over the square root of t squared minus 6t plus 13. And the problem is, you see, we can handle it as long as it's a binomial like a squared plus u squared under there, or it's a squared minus u squared, or it's u squared minus a squared. As long as it looks like one of those three, we can handle it. This doesn't look like any of those, so what we do is try to make it look like one of those by completing the square. So this is equal to the integral of dt over. This is t squared minus 6t, and then you fill in this box to make it a perfect square, knowing there's still 13 here, and you have to subtract what's in the box or you have changed the problem. So the whole question is, do you remember the magic number that makes a perfect square out of t squared minus 6t?
933 squared.
Yeah, remember half of 6 and square it? Remember those days when you used to solve quadratics by completing the square? Take half the coefficient of t and square it? But see, you got to remember, I got to do that too. Because otherwise I've changed the problem. So what does it become? Well, the t squared minus 6t plus 9 can now be written as a square. What is this as a perfect square?
Plus 3.
T minus 3. Okay, now if you take the 13 minus 9, you can see this problem was rigged so you wouldn't get discouraged. Because that's a nice number too. So you see, technically what we're doing is we're letting u be the t minus 3. Okay, and the a is going to be 2. And then it fits perfectly the first one, a squared plus u squared, or u squared plus a squared. Of course, you do have to remember, all this stuff. But that's, I think, fairly obvious. So dt and du are the same thing, so I can just put du there in place of dt. And right here, I can go u squared plus 4. Or u squared plus 2 squared, if you like. And now, could you keep going? Because you know the substitutions for these, right? If I remember right, the square root of a squared plus u squared was a secant theta. Remember? And there's that little right triangle to go with it, if that's helpful. And if it's really helpful, we said you could even write those down, right? But you're not supposed to tell that I let you do that. Is that sufficient for completing the square? I mean, it's not a big deal. And you see the purpose, right? I got to make it look like one of these. Anything else about the test?
Are we gonna do any of that Simpsons rule?
Yeah.
Over one of
Which direction? Where you use it to approximate, or would you use it to try to decide what value of n is going to give you the approximation you want? Pardon?
approximation.
Doing the approximation? It's just a matter of filling it in. I don't know. I tried not to choose too many intervals so it would take forever. Now remember, when you do Simpson, you got to use an even number of intervals for it to come out. But do you remember what Simpson looks like? What's the coefficient? You got that all down somewhere? I mean, do you know Simpsons rule in general? Then it's just a matter of filling it in.
What's the general formula?
What's the coefficient? h over 3. Remember? Then you start at f of, oh sorry, f of
0.
x sub 0. You know, you start at the left endpoint. Then you go to
4.
4. Then you go to 2. And so, to me, 90% of this is just trying to pick the right x0, x1, and x2, but that depends on how the division of the intervals take place. And then there's a 4 again. And then a 2. And you continue that way. And the last one, f of xn, is by itself, just like the first one is. And what's the one just before it, a 4 or a 2? 4. Yeah. Okay, let's just suppose we're doing something like, I don't know, x over natural log of x or something. And maybe we're going to go from 1 to 9. And we wanted to approximate that using, I shouldn't go from 1 to 9 because natural log of 1 is 0, and then it's an improper integral, and that's not my plan here. Let's go from 2 to 10. Okay? That's what happens when you ad lib, but you got to be careful and look at what you actually wrote. But that should be fine, right? Okay. Now, when you go from 2 all the way to 10, let's suppose they wanted you to divide it into 4 subintervals. That would be nice, right? Because then that wouldn't take a ton of work. And they'd even come out pretty nicely. Because that would be 4 of them, wouldn't it? You know, you have some curve up here. Okay, what would the numbers be? All right, so if you fill in Simpson, what would h be? Well, h is always this distance here. So what is it? So it would be 2/3, right? And then I'd have to take f of 2. Then I'd have to go 4 f of 4. Then you have to go 2 f of 6. And then another 4 f of 8. And then end with an f of 8. And then just do it. Of course, f of x would be this x over natural log of x, right? So you just evaluate it at 2, and then evaluate it at 4, multiply by 4. And usually with Simpson, we discovered that the sum sequence isn't a real aid unless I told you to pick 24 intervals or something, then it might be worthwhile. But I do want to get home eventually, so I probably won't pick 24. 4 is pretty easy, isn't it? Anything else? Too many questions. You're getting me nervous here. The test isn't that bad. I took it. I got a C minus. That's one of my better ones, so hey, you're good. Got to get that up to a C, though, because I want to pass this course finally. So I can move to Calc 3. Okay, then I just wanted to introduce a little bit of 6.2 so you know what you're in for. Your assignment for next time, of course, is 6.1. You know that, right? Where you're going to play with some of those area things, which really aren't too bad, because we discovered that if you want to find the area between two curves, it doesn't matter whether the curves are both above, both below, one above, one below. It's always done the same way, which is kind of nice. Curve on top minus curve on bottom when you set up the integral. Okay, the next thing we are going to do is section 6.2, and it's called Solids of Revolution. And there's a little more in that section than you can usually do in just one setting. And so I figured if I get it started, then I can easily finish it without too much stress the next time. Okay, A is going to be a little introduction. And that's trying to give you an idea of what we're trying to do. Oh, you want to see it? I thought it might be easier if you didn't see my horrible drawings. Okay, basically what we're going to be doing, although this won't be our initial problem, is take some curve in a given interval, maybe in this case from 0 to A, okay? And what that does is makes a certain region between the curve and the x-axis. This is y equals f of x. Now, can you picture taking this piece and spinning it around, say, the x-axis? Picture spinning it around. Now, I do have some stuff on here that might help you to see it. We'll see if we can find a decent one here. See how Dr. Tellman did. See here, right there, is, he put it in a little box because I think he's using maple, so that's the way it likes to set it up. But here's that region, okay? Now what he wants to do is take that region and spin it around the axis, and that's what happens over here. See that region being spun around that axis, generating that solid figure. And what we're after is, how can we find a way to find the volume of that solid that's being generated by that rotating piece? See, it started out as an area, right, that we're rotating around, and it generates a solid, and we're looking for a way to find the volume. Okay, if we, here's another one. This is kind of an oddly shaped region. And he doesn't do too badly there. You can kind of see the rotation going on around there. Okay, let's see what else he's got here. More rotations, okay. All right, we'll go and see if we can hit the method a little more. Jonathan usually does a pretty good job. We'll see what he's got. Well, he says you got to go find what you want, okay. Oh, solids of revolution. There it is, volumes. Let's see what it does. Okay. What he did is he's showing, you know, here's the basic curve going up here, and here's the region that would be defined, let's say, in the first quadrant. And then he spins it around, and you can kind of look at this, so you can look inside like that. So it kind of looks like a horn. And that little green one is trying to show you the method we're going to use. Can you think of filling this solid region with a bunch of little discs, and then you find the volume of that disc, and then you just keep stacking them sideways till they fill the figure. Okay? I've got something else I can show you here too in the box, which gives you a little bit of an idea of what's happening. See right here, you can see is a solid figure, okay? And if I want to find the volume of this, one way to do it is divide it into all these little discs. It's supposed to come off. Something seized up. Come on. I think the little peg in the middle swelled. This may or may not work. I have to work on that. But you can see here's the little disc. And they keep changing size, of course, as you stack them up in this figure. But you see something like this, which is called a little disc, you can actually find the volume of, because technically it's a what shape in geometry?
Cylinder?
It's a cylinder, isn't it? Because it has to have some thickness to it, otherwise I couldn't hold it in my hand. Is it easy to find volume of a cylinder?
Pi r squared times h.
Yeah, just pi r squared times h.
Right.
So I find the volume of each of these little cylinders, okay, each one is a little different. And then if I add them all up, I've got a good approximation of the volume of the solid. Can you see where it kind of parallels what we did with area? Because there we divided it into rectangles and then added up the areas of the rectangles till it filled the figure. And the more rectangles we used, the closer we got. And if we wanted to get an exact area, we had to take a limit as n went to infinity. All this same thing is going to happen again, but you do it to little cylindrical discs instead. Okay, I always like to make sure that what we're about to do has some credibility. And so therefore, we're going to start with an example where you don't need calculus to do it. And we'll get the answer, and then we'll use calculus and see if it actually gets the right answer. But before I leave this, one thing you'll get a chance to do is a little bit of drawing. And what we like to do is kind of show the 3D effect. And then inside of here, you can think of all little discs, right? Because I'm rotating it around. And they're stacked up from left to right. And if I find the volume of each of these little discs and add them up, I'll get an idea of the volume of that solid that I generated. Okay, then the B part is an illustration using a right triangle in the first quadrant rotated around the x-axis. Now I think to make it look maybe more realistic, we'll do y-axis first. So it's a right triangle in the first quadrant, and we'll rotate it around the y-axis so that it looks like you're used to seeing the figure. So number one will be the drawing. So here's the x and y axis. And I think I'll make the height of this triangle 4. And I'll make the other leg 3. Because then you know it's kind of a nice triangle, namely a what? 3, 4, 5. Now can you imagine taking this and spinning it around the y-axis? Now when it spins around, it's going to run right smack into that xy plane again, leaving that image. But to show the rotation, we do this. Now I started with a figure like that because you can see if you start with a right triangle and rotate it around the y-axis, what did I get? A nice right circular What is that? Solid. Figure is a cone. I don't need calculus to find the volume of that figure that I just did, because number 2, we can get a quick geometric solution to the volume of the cone. Do you remember the formula? Well, even if you didn't, it wouldn't be hard to look it up. Volume of a cone.
1/3.
1/3, very good.
Base times height.
Area of the base, pi r squared times the height. That's the official formula for a cone. And the way I constructed it, I think we can fill that right in. Because what's the radius of that cone going to be, based upon my picture? 3, so it'd be 3 squared, and the height is
4.
And so the answer is
9.5.
is
12 pi.
12 pi. Okay, we want to save that, because even though we're going to pretend we have no idea how to find the volume of a cone, and we're going to let calculus do it, if our method has any credibility, we better get what? 12 pi, because geometry says the answer is 12 pi. Okay, so number 3 is going to be the calculus solution. Now, in the calculus solution, we're going to take that cone and do what based upon the stuff we looked at in the introduction? We're going to divide it into circular discs. Like in this one, here's the sample disc. Here's another one. Of course, we want to fill this right up with all those little discs. We'll find the volume of one of them, add them up till they fill the cone, and see what it is. Okay, typically when we do the calculus solution, we just draw one sample disc and work with it, rather than draw a whole bunch to distract us. So here's the picture again of the cone, and this will be our sample disc right there. Okay, the first thing we have to do is find the volume of the sample disc. Got to get that volume first. Well, since it's kind of a random disc, we go to the edge of it here, and it's in a rectangular coordinate system, and we label that point x, y. That's usually the beginning when we're looking for volume of the sample disc. Okay? All right, if that's my sample disc, then what is the radius going to be? Oh, we need volume of a cylinder, because that's what every disc is. And V is what? Cylinder. Do you remember that one? You know, you have this. There's a typical little cylinder. Now ours aren't near that tall, but they have some thickness to it. How do you find volume of a cylinder?
Oh, it's just area of the base times the
So
height.
it's pi r squared h, right? Very simple little formula. All right, what is the radius of my little disc here? It's x, so volume of my sample disc is going to be pi x squared. But now, what do I do for the height? You see, if I pull that thing off like this, it looks more like a coin, doesn't it? If I pull that disc out and just set it down here. Now this is the radius, but it's got to have some height to it, otherwise.
Height is
Right? The total height of the cone divided by the subintervals?
But how many of these discs are going to be in there? Well, if I want to get the area or the volume exactly right, I have to stack how many in there?
Infinite number?
An infinite number, right?
Oh.
Now, do you remember when we did the rectangle problem, when we were looking for areas? What do we call the base of each rectangle?
was b minus a over n.
Okay, and what did that represent?
The integral.
I know, but what was it called originally? Delta x, yes. Remember change in x? It was just a small change in x. And if you want to calculate it, you take b minus a over n? Yeah. So you're on the right track, but this time, because of the way they're being stacked, the thickness or height of the disk is not going to be a change in x. It'll be a... That's what we write for the thickness. Now later on we can talk about what delta y is, but initially it's just a very small change in a y distance, right? And that's going to be the height. Okay, now that's the volume of the sample disk right here, which we need to keep our eye on. So what is going to be the volume of the cone itself using those little discs right there? Well, I have to take the volume of how many of these?
Infinite?
I have to take an infinite number of those, starting with y equal to 0, and ending at y equals what? Do you remember where the top was? 4? So I have to take all the possibilities I can from 0 to 4. So for the volume of the cone, we have to take an infinite number of discs like this and add up the volumes. Isn't this what we use for adding up? Summation. And the summation has to go from where to where? Well, I running from 1 to n, because we're going to use n discs. And this would be pi x sub I squared delta y. So I put the little subscript on right here because this is going to be the ith disk, and I runs from 1 to n, and I'm counting them. This says I'm going to add them up. Now I have to do one more thing to get the volume of the cone. I can't just add those because there's n of them. What do I have to do at the end? Well, I need an infinite number of them, right, to really fill them up, because they have to become very thin.
Limit.
I'm hoping you can see the parallels to what we did with area last semester. You know, we split it into rectangles. We said to get it exact, we had to take an infinite number of rectangles. So what did we do? Divided it into n rectangles and then took a limit as n went to infinity. Same sort of a deal here. But now we know exactly what this is going to turn into. Because when you take a limit of a sum like that, remember what it turns into?
Integral.
A definite integral. What are the limits of integration? Well, just look at the picture. It's 0 to 4. It's in a y direction. Got to take all the discs I can fit from 0 to 4 when I stack them. And then I have pi x squared. And what does delta y turn into? Now, right away, there's an issue that's going to happen every time. Because I'm integrating with respect to, but the variable is, and so you always have to take time to get this part in terms of y so you can integrate. The variables have to match. So it's back to the drawing. See where x and y are? That's why I put them on. How can I get y in terms of x? Well, I don't care where I draw the disk. Isn't this little edge always along that line over here? Isn't it? And as long as you're on that line, can't you find a relationship between x and y? And then you can just solve that for x and you got it. what point is this really up here? I mean, I put a 4 there and I put a 3 there, but what's the point? It's 0, 4. And what's the point down here? Okay, do you know how to find an equation of a line through 2 points? Yeah, it's really easy, so it's not going to be hard to get x in terms of y. So the next step is must express x in terms of y. Okay, the 2 points I have are 0, 4 and 3, 0. So the first thing I need is the slope. I think we can do that in our head, right? What's the change in y? 4 minus 0 over 0 minus 3, which would be?
Negative 4/3.
So y has to equal negative 4/3 x plus, and b is the y-intercept, so that's easy. There it is. But that's y in terms of x. The reason I did this is I need x in terms of y. So I just multiplied everything by 3. 3y equals minus 4x plus 12. So 3y minus 12 equals minus 4x. Divide by minus 4 and you get x equals what? Negative 3/4 y plus 3? That's what I need. Okay. It's still up here. That was just a little side trip so I could do the integral. So now officially it's from 0 to 4. And then I need pi. And then I need x squared. So I have to take negative 3/4 y plus 3 and square it, and then dy. And if I can integrate that, I should have the answer to the exact volume of that cone using calculus. And since I could do it using geometry, I bet the answer to that integral is what?
12 pi.
12 pi. Do you believe me? Well, in the interest of time, because I want to let you get started on the test, we're just going to do that one with the calculator just to verify that we're okay rather than do it by hand. Of course, we could do it by hand just in the time it takes to zoom in on that thing, right? Okay, F3 number 2. I wish to integrate what? Pi. And that's times negative 0.75 y plus 3, the quantity squared, and I want to do it with respect to y. And I want to go from 0 to 4. I think that looks okay, doesn't it? Calculator shouldn't care how I enter the negative 3/4. Anyway, I'll press enter. Look at that. So what does that say? The method has potential. Well, when are we going to use that method? When that solid is an odd shape that doesn't fit any formula in the geometry book? So we aren't going to be using it on a regular basis to find volumes of cones. But I wanted to on the first one so you could kind of have an idea how the method worked, what the theory is, and see that it does actually work. You do get the right answer. Same thing you get when you use geometric formula. Are you okay? So now are you all confused for the test sufficiently? Okay, but I wanted you to have a little bit of an idea of just how that worked so that on Thursday I can just jump right in and start doing some problems where there's no alternative other than using the calculus, because geometry can't cut it, because they're not familiar figures. Okay, feel free to take a break when you want to. I'll distribute the tests, and that's the only other thing on the agenda. When the test is done, you can... But if you need a stretch or whatever you need to do, feel free. That's no problem. Think of you